Thank you for the introduction. Today I'm going to talk about quantum oracle synthesis with an application to QRNG. First, I would like to recognize my collaborators. Oh, there they are. My graduate students, Avi Sinha, Jesse Henderson, and Elena Henderson, and also my faculty collaborators, Eric Larson, who's here at SMU in the CS department, and my longtime collaborator, Mike Miller from the University of Victoria in British Columbia, Canada. So this is kind of the outline of my presentation. It's really in two parts. The first part is on quantum circuits and oracles. So I'm going to define what an oracle is, and then I'm going to show you two oracle synthesis methods that our group has produced with some experimental results. And then I will show you an application of oracles, and that application is in the area of quantum random number generators, and in particular, the weakly random source for that. So I know this is an area everyone may not be too familiar with, so I'll give a general overview of different types of random number generators, including what a weakly random source is. And then I'll talk about how we actually synthesize the user-defined probability mass function as an oracle such that we can use a commercial quantum computer as a QRNG. So this is probably not news to many people, but I just want to make sure we're all on the same page here. I like to think of quantum algorithms or circuits in their graphical form based on just a figure that's embedded in a Cartesian plane, wherein the vertical axis is discrete and shows the number of qubits in the algorithm, and the horizontal axis is continuous, representing the passage of time as the quantum state evolves as it progresses through these operators that we call quantum gates. So there are several well-known quantum algorithms. This is just a few samples, and I have shown their quantum circuits here in graphical form. And the thing that I want to point out about these four circuits are these large unitary transforms labeled U inside each of these. These U's are user-defined functions that are synthesized to implement these algorithms. And in particular, even though these are well-known patterns, it is often the case that the user must synthesize unique versions of these functions U. For example, in Grover's search, this U function changes depending on the database you're searching over. And typically for small circuits, this could be done manually, but as the number of qubits grows large, this function can become very large, and that motivates a method for automated oracle synthesis. So it's these U functions that can vary in particular applications that we refer to as oracles. I would also mention that many times a user may initially have a specification of these functions in an irreversible form, meaning it's not a bijection, and it may even be incompletely defined, meaning that there aren't domain and range pairs specified for all possible values. So our tool has to create these unitary transformations for which these functions are embedded. So let me give some definitions based on that. We call the oracle function the initial function that a user wishes to synthesize into the unitary transformation. And this can be a function over real values or floating point values, but since we're dealing with qubits, we express the domain and the range values as n bits for the domain values and m bits for the range values. Now, clearly, if n is not equal to m, this is not a bijection. It's not even irreversible in that two unique values in the domain may map to the same value in the range. Furthermore, there may be an incomplete specification in that some possible n-bit values and their corresponding m-bit range values aren't present. So the first thing we do is create something called an embedding function, denoted as f sub e. And this isn't really new news. I'm sure you all have probably done this before, but that's accomplished by adding ancilla bits to the domain values and garbage bits to the range values. And these are added and defined in a very careful way to cause this embedding function to be a bijection. It must be a bijection before we can then synthesize the transfer function for the oracle u sub f, because if it's not a bijection, u sub f will not be unitary. And as you all know, that's required. So ultimately, we synthesize the gates that implement this oracle function, and it is represented by a transfer matrix of size big N by big N. So let me give some examples of how we can define input specifications. And I've chosen a very simple one for this presentation because it's easy to understand. Some of you may have seen this before. It's a tabular form. It's essentially the truth table specification in conventional binary switching bits. Here we see that this first array represent the bits of the domain variables, and these two bits on the right represent the range variables. And this is not really compact, although there are some ways to compress it slightly. For example, in this format that was defined back in the days of electronic design automation research, we see that a dash can be used to indicate that this value is both 0 and 1. So there's a little bit of compaction here. And this is typically the form that a user would input. Another important thing about this form is that from a conventional logic point of view, this represents a sum of products form. That means that if you were to implement this function in conventional logic, you would create AND gates for each of these values on the left, and you would add them together with the inclusive OR. Again, this is a simple way to express functions. Other representations are much more efficient, and our tool does support those. One of those is the QMDD that was presented by my colleague Michael Miller and myself in 2006, or Verilog netlist. But for ease of understanding, we're going to stick with this PLA. So the goal is, given this input specification, we want to produce the oracle function as a cascade of gates. And I'm going to show you two methods. The first one synthesizes the oracle with a minimal number of qubits required. So if you look at the absolutely minimal number of qubits, that would be for the case where we have more bits in the domain than we do in the range, a function that looks like this, where we added n minus m garbage outputs, because we know that we have to have the same number of lines on the left and right hand side. This has to be a square unitary transfer function. In the converse case, if we have more bits specifying the range values, then we would need to add m minus n ancilla bits. So we can't just add those bits arbitrarily. We must also assign values to those bits to cause them to result in a one-to-one function. And we have a method to do that. There's a variety of ways this could be done. We have one method called reduced truth table, RTT method, that really is taking that user-specified irreversible function and embedding it into the embedding function. And I've got the rules for how that's done here that I won't belabor, but you're welcome to see that technique in this paper down here at the bottom. There's some heuristics. For example, we found that as we make assignments to ancilla and garbage bits, it's advantageous to cause specific function, domain, and range pairs to have a minimal Hamming distance. That tends to help with reduced circuit complexity. But in any event, after we perform this RTT, we now have our embedding function, and we're ready to synthesize the oracle. And this leads to the first oracle synthesis method that minimizes qubits. And here are the steps written out in words, but I think it might be easier to just see a graphical example of this. So let's assume that this is our input truth table in the PLA form that we wish to synthesize into an oracle. And by the way, this is the embedding function. So it's already been converted to a bijection at this case. So the basic idea for this method is to traverse each entry in lexicographical order here and to try and build up an identity. So we would start with this first one, and in order to make this an identity function, we see that we would need to invert these three ones. So we would add these three poly-X gates or NOT gates, quantum NOT gates. And that would then leave the remainder function to be synthesized. But at this point, we have converted this top entry into an identity. 0, 0, 0 maps to 0, 0. The whole concept is to convert the original embedding function into an identity. So we have to recompute this residual function to be further synthesized. And we next move to the next entry. And in this case, we see that whenever we have a 0, 0, 1 that we wish to map to 0, 0, 1, we need to use these two control points for these two ones, and then do an inversion here to get a 0. And that would then cause that term to become an identity. And so we continue doing this, working from the output to the input. You can implement this algorithm from the input to the output as well. And there's even a bidirectional method where we can go both directions at the same time. I'm just showing you one unidirectional method at this case. Whenever that's done, this truth table gets updated again, and we just do the process over and over until we have our embedding function, represented as a cascade of Toffoli gates, C naughts, and knots. At this point, it could be even further synthesized into lower level atomics, but we now have our reversible oracle. And the second method is a method that preserves the domain qubits. And if I go back up to the earlier slide that showed the examples, I want to point something out. Many of these well-known patterns use the domain variables after the oracle has been evaluated. They require to have copies of the domain variables. And for that reason, this second method is applicable in that case. So in that case, our oracle is going to use n plus m lines. So it's simply the number of bits for the domain plus the number of bits for the range. And we don't have to explicitly compute the embedding function for this technique. That happens automatically as we synthesize the oracle, and you can see that the domain variables are preserved so that they're available for further processing. So the key idea behind this is to convert the SOP. Remember, I mentioned that the PLA format is a sum of products with an inclusive OR into an exclusive OR sum of products. So it transforms the switching function into this ESOP form. The exclusive OR is addition modulo 2 rather than the inclusive OR. There's a variety of algorithms that have been developed to convert SOP to ESOP, one of which is Exorcism 4 that was written by my colleague Alan Mashenko at Berkeley. But you could use any method you wish to do that. And then we showed again back in 2007 that simply by converting these SOPs to ESOPs, we have a very simple way to synthesize oracles. So let me show you an example of that. So in this case, we're going to start off with the ESOP. So this has already been converted from a sum of products to an exclusive OR sum of products. And here's the function that a user would wish to specify. Now, this probably isn't the best example because it has 3 domain bits and 3 range bits. These numbers of bits could be different and it would still work just fine. It is not required to have the same number of bits in the domain and the range. But the way this works is that we process again each of these values. I would note in this case, it really doesn't matter the order in which these are processed for this second method. So the idea is that we have n plus m lines. So A, B, and C are the 3 domain bits. D, E, and F are the 3 range bits. And these 3 range bits are initially initialized to ket 0. And we see that we have in the domain a dash, so we do nothing. We have a 0 here, so we want to convert that to a 1 to activate this control point, and then we convert it back. And here we have a 1, so we put a control point here. And these 2, D and E, were initialized to 0. So all we have to do is invert F whenever we have this condition. And then we continue with the residual function. So in the next case, we see that whenever we have this 1 on B, that we need to invert D and we need to invert E. Now, one of the powers of this method is that, as I mentioned, you can do this in any order. You don't have to start from the top and move down. That's because conversion to ESOP causes a disjunctive cover to occur for this switching function. So when I convert one of these lines in the table, it will not affect anything downstream. I don't have to worry about keeping track of values of D, E, and F. I can do all of these independently. So if you continue the process, then you will wind up implementing the function variables, and you'll see that the domains are preserved. There's an even number of poly x's here, so A, B, and C equal A prime, B prime, C prime. So we compared these two methods using just some standard benchmark functions. And we compared them with 3 metrics, one called circuit complexity, which is roughly equivalent to quantum cost, the time to synthesize, and the required number of qubits. We compared this method 2, the ESOP method, with method 1, which is the table method that requires the function embedding. Now, the ESOP method doesn't require function embedding at all, but we went ahead and ran that case anyway because we wanted to get an apples to apples comparison between ESOP and TBS. In other words, we wanted to add in the overhead of RTT, even though it wasn't needed, just to compare fairly TBS and ESOP. So in performing that comparison, what you see here are several benchmark functions of various sizes. So for example, this first one is called square 5. It has 5 domain bits and 8 range bits. There are some slightly larger ones in here. But anyway, what you can see is that the ESOP method, in terms of circuit complexity, which is roughly equivalent to quantum cost, is much lower for the ESOP method than for TBS. In fact, it's lower by an order of magnitude. Even if we add the overhead, which again is not needed, even if we add the overhead of RTT in. So ESOP wins for circuit complexity. Next, we're going to look at time to synthesize. And again, ESOP came out on top. You can see in microseconds the time to synthesize these circuits. By the way, we have synthesized circuits with ESOP that have as many as 100 domain variables. So it's quite scalable. And the primary reason for this is we don't have to compute an embedding function, and we can implement those cubes in any order that we wish. However, for minimizing qubits, which we all know is extremely important today because there's very few available physical qubits on today's machines, the method 1, the table-based synthesis, outperformed. It did about 50% better on average for all these functions. So this is kind of the trade-off. It depends on what the user wants. Circuit complexity, qubit count, synthesis time. Synthesis time is pretty short for any of them in wall clock time. So that's the summary of the two Oracle synthesis methods. TBS is better for qubit count. ESOP is better for circuit complexity and time to synthesis. And as you might have already thought, we are looking at hybrid methods that take advantage of both. So now I want to talk about an application of Oracle synthesis. And in particular, I'm going to talk about quantum random number generators. Random number generators are crucial elements in many different contemporary applications, such as cryptographic systems and their implementations. You may have used random number generators in Monte Carlo simulators. They're commonly used to generate keys and passwords or nonce and salt values. And in the area of quantum informatics, they can be particularly useful if you have prior information about your data. For example, if you can think about Grover's algorithm, you see that the domain variables are initialized to 0 and then immediately applied to a bank of Hadamards that place those into perfect superposition. So if we were to measure one of those bits after they're in perfect superposition, we've essentially, from a statistical point of view, created a uniform distribution. So we start off with a uniform distribution, not only in Shor's, but many other algorithms. If we know something prior about the distribution, we can enhance performance of these algorithms by synthesizing a non-uniform distribution instead of that bank of Hadamards. It turns out that generating high-quality random numbers is a really hard problem. It's very difficult for humans to generate random numbers. And in fact, you really can't write an algorithm to do it because algorithms are always deterministic. But in quantum state measurement, it is an observation of a variate of a random variable. A standard projective measurement, as you know, will collapse to one of the measurement bases with respect to the square of the magnitude of the probability amplitude. So we're going to take advantage of that by building quantum random number generators. Now, I promised I'd give a little bit of background on random number generators. So I have this one slide, and that is the difference between a true random number generator versus a pseudo random number generator. Both are important, but a true random number generator comprises a component called a weakly random source, followed by another component called an extractor. And the important thing to note about true random number generators is that we obtain the random value ultimately from some natural process. I'll talk a little bit more about true random number generators in a minute, but I want to contrast those to pseudo random number generators. Pseudo random number generators don't really generate random numbers at all. They're really just a deterministic function. However, if you were to observe the output of a series of values from a QRNG, you would see that its sample statistics mimic those of a distribution. So they're really deterministic. They can be recreated, but they appear to have characteristics of a random distribution. And those are used commonly today in cell phones as scrambler codes and Wi-Fi routers for the same reason. They're useful because two stations can generate the same pseudo-random sequence that appears to be random but isn't really and has desirable propagation characteristics. True random number generators are generally built with the goal of having a uniform distribution. But more and more, there is a need to have other types of arbitrary distributions. For example, in some of the post-quantum cryptography codes like Crystal's Kyber key exchange, there is a need to generate a lot of binomially distributed entropy. So that's the idea here, is that we're going to build a TRNG wherein our physical source of randomness is the quantum measurement. And so the weakly random source comprises this inherent quantum mechanical characteristic due to Born's rule and the measurement. And then after the measurement collapses it to a conventional bit, we have to perform an extraction, which is like a correction function. You can think of that as a random variable transformation, or you can think of that as removing bias and determinism that is introduced by measurement. So here are some acronyms. I won't go through all of these. I've mentioned several. When we compare our results, though, we're going to be using the Kullback-Leibler divergence and the Jensen-Shannon divergence. These are just two ways to compare an ideal distribution to our synthesized distribution. So our idea is to use a quantum random number generator implemented in a quantum computer, a programmable quantum computer, to build a TRNG, a true random number generator. So conventional electronic true random number generator may have some natural source like a semiconductor device noise or radioactive decay embedded in here, and then it'll have the extractor function and produce variates according to some probability mass function. In our case, we're going to start off with user-defined number of n qubits and a user-defined probability mass function. And we're going to synthesize an oracle that evolves these qubits in a basis state into a superimposed version of the desired probability mass function. And it's going to be of this form. This is just really implementing a user-defined probability mass function as a single quantum state of n qubits. And then when we perform a measurement of these n qubits, we sample a variate from this distribution P of X. And that's done by receiving the user-defined probability mass function and encoding it in the probability amplitudes of the quantum state. Now, you may have noticed there's a square root here, and of course that's needed because when we measure, we're going to receive the probability that the qubit's won with this probability amplitude squared. So it's necessary to encode the square root of the coefficient of the probability mass function. And then we implement that transformation in our oracle in this way by just, it can be shown in our paper that it's really just a series of rotations about the y-axis. And there is a relationship between these rotation angles alpha and the normalized values of the probability distribution that we wish to synthesize. So we end up with a quantum state representing a user-defined probability mass function. So in this paper, we called this experimental tool Flex QRNG. So it allows the user to specify the desired probability mass function with a desired number of qubits in. And if we use n qubits, then we have 2 to the n different discrete variates that we can sample from our probability mass function when we measure it. And then we automatically generate the oracle in probability amplitude encoded form that corresponds to this probability mass function. So here are the steps. We receive the probability mass function. We perform amplitude normalization. We encode it into the quantum state. That is done through an oracle that represents the PMF. We also perform optimizations to reduce circuit complexity and map it to a specific hardware backend, such as the IBM quantum computer, or whatever your favorite quantum computer is. Here's an example. So this is an example for the binomial probability mass function. The binomial probability mass function is just the discrete form of a normal or Gaussian distribution. So here the user has specified, I want to use 5 qubits, and here is the 32 or 2 to the 5th different coefficients of the binomial distribution. Now we first have to normalize those amplitudes by dividing by the Euclidean norm, because this is a unitary function that we're going to be implementing. But once we have this normalized binomial, we can then use our oracle synthesis methods to produce an amplitude encoded version of the probability mass function. And then we also apply optimizations, and you can see the resulting quantum circuit we produce for a 5-qubit binomial probability mass function. And here the measurements, every time you measure, you would receive randomly generated variate from the binomial distribution. We performed a series of experiments using the IBM Washington noisy simulator. We needed the noisy simulator because if we did this with the perfect simulator, our specified probability mass function would be identical to the one we synthesized. So I mentioned that we were going to judge the quality using some metrics, the Kullback-Leibler divergence, which compares the ideal distribution, the one the user specified, to the one that was implemented in the oracle. There's also a statistic we can use, the G statistic. And we also looked at the Jensen-Shannon divergence, which is really just a function of Kullback-Leibler. But Kullback-Leibler can get you into trouble, because if this value in the parentheses is less than 1 and you take the natural log, it can jump down to negative infinity. So Jensen-Shannon kind of takes care of that for us. In any event, it's probably easier to just look at the generated distributions versus the ideal distributions than to make sense of those metrics. So what you see here in the first example is the uniform distribution specified by blue, and you can see it's perfectly level here. And each value is normalized to 1/32 because we have 32 bins, 5 qubits. And for about 34,500 shots, we got this type of result for our synthesized distribution. Here's the binomial. Here's a triangular distribution. Of course, if we increase the number of shots, the noise goes down. Here is an arbitrary bimodal distribution. Here's a totally arbitrary distribution. It's got many different local extrema, we thought would be a harder case, but this demonstrates the power in that we can generate any probability mass function, even those that are non-parametric with this method. Here are the quality metrics, and you can see things like number of gates and depth and those different statistics and p-values. But I think you get the idea of the approach here. I hope you do. So this concludes the technical part of my presentation, but I really am looking forward to letting this audience know that we here at my university have just opened 2 tenure track positions. We want to hire people in quantum informatics. One of them is at the endowed level, and the other one is at the introductory assistant professor. So if you're interested in working with us and like this kind of work, or have other quantum work you want to pursue, please check out the faculty listings for these positions or contact me directly, and I'll be happy to give you more information. So as a summary, then as the number of qubits increases, we'll need automated tools like oracle generators. And I showed you a use case wherein we produced a quantum random number generator. So at this point, I'm happy to take questions.